Now let's look at a situation where we are adjusting the loss. So let's look at the loss. So let's define, let's say L sub B of a batch. So the sub B just means it's the loss for a particular batch. So in fact, let's just say that, well, we know the loss we've been using so far is the mean squared error, right? So that's going to be the sum for all B in the batch for all xy in the batch of f of xy, f of x minus y squared all over the size of the batch. It's going to be the mean squared error. The idea is we go ahead and define, we don't use this loss directly. Instead, we're going to use a new loss. So our new loss, I'm going to call B prime of the batch. And that we'll use some linear combination of, well, let's just use the old loss. And then we're going to add some penalty. So we're going to add a penalty based on the complexity of theta. So we're going to do some regularization on theta, such that if theta is too complicated, that's going to increase the loss. So the loss can be increased either because our mean squared error goes up or because theta gets to be too complicated. And we'll have some scaling factor here. So this scaling factor here is just going to make sure that these two are sort of in the same range. So what might this penalty look like? If we had a d-degree polynomial, right? So f of x equals some summation from I equals 0 to d of a sub 0 of a sub I x to the I. And so in this case, right, theta is basically all our a sub i's. What would it mean to have a complicated theta? Well, imagine we have a 10-degree polynomial, right? So we've got some data points to fit. Let's say we have 10 data points. 2, 3, 4, 5, 6, 7, 8, 9, and we'll get one more here. Okay. So with a 10-degree polynomial, we could have a 10-degree polynomial that goes exactly through every line. So it might be this. That might be our 10-degree polynomial that fits this. Do we think that's going to generalize well? I certainly don't think so. I think a different polynomial might generalize better. Something like that. That doesn't exactly go through every point, but is simpler, right? This is a 3-degree polynomial, roughly, where this is a 10-degree polynomial. And I think the 3-degree polynomial will fit better. Why do I think, I mean, for what reason would I think the 3-degree polynomial fits better? Occam's razor, right? Occam's razor, the way I describe it is prefer simpler explanations. Prefer simpler explanations, right? So it seems more likely that you'd have a degree 3 polynomial that almost fits all these than a degree 10 polynomial that fits them all exactly. So how could we somehow use a 10-degree polynomial and this loss function in order to force ourselves to try and get this degree, force ourselves basically such that a sub 10, a sub 9, a sub 8, a sub 7, a sub 6, 5, 4 are all 0 or very close to 0. And so it's only a 3, possibly a 2, and a 1 that are bigger than 0. Well, what we could do is we could define our penalty like this. We could say, and remember again, the theta is just our collection of a's. Well, here when we're looking at this, we're saying how far away is f of x from y? How far away is y hat from y? And we're going to penalize as to how far away it is by taking the squared difference. Here, let's penalize how far away it is from 0. So however far an a sub I is from 0, that's going to be our penalty. So we could have well, how far away is a sub I from 0? It's a sub I away. So we'll just take a sum of the a sub I squareds. So assuming we set our gamma appropriately high enough, then that's going to force our learning to, that if we have, let's say, a 0 gamma, then we might get this really squiggly line that exactly fits everything. If we had a high gamma, then it's going to give us something with it. If we have a super high gamma, what's going to happen? Well, maybe we'll end up with just like a horizontal line, right? Every a sub I is 0, except maybe a sub 0 is some number in here, right? And if it's high enough, then our penalty completely outweighs the loss here, and we'll just choose to make all the a sub i's a 0. So this, by the way, this squared here, this whole thing, this is called an L2 norm. An alternate we could do is we can say, I don't know why we're doing this squared. All I really care about is the magnitudes of the a sub i's. So alternately, we could say it's the same summation, but just of a sub I. That's not quite right, though, because we might have some positive a sub i's and some negative a sub i's, and they would cancel out. So we could go ahead and do the absolute value. That is called the L1 norm. And these are both common measures, but the L2 norm is most often used. So this is a change to the loss function. As you're going to see in an in-class assignment, the L2 norm is actually equivalent to using the original loss function with a different optimizer. So our optimizer normally looks like theta equals theta minus lambda times our gradient. But if we switch to this loss function, which includes this penalty, then, so let's see, this is with, I don't know why I called this B prime. I really want to say this is L prime sub B. So this is with L prime, and that's equivalent to theta equals 1 minus gamma lambda theta minus lambda the gradient. And this is with the original L instead of L prime. So this is with L prime B, and this is with LB. This is a simple matter of algebra to get us here. But what I just want you to note here is what this does is says it is equivalent to using an L2 norm with a penalty as it is to doing this, which is called weight decay. Why is it called weight decay? Because every time we go through and update theta, we're going to say, okay, instead of theta being what theta used to be, and then subtracting a percentage of the gradient, we're going to reduce theta. So 1 minus gamma lambda is chosen to be less than 1. So theta now gets shrunk by a little bit, and then we apply the gradient in whatever direction. So every time through the loop, we are reducing our parameters. So that's a natural tendency to be forcing them towards 0. So it's a different way of doing it than this. So what we're basically doing is we can either do this with a penalty on theta, or in the specific case of the L2 norm, we could do weight decay here. And those are equivalent.